All right. Good morning, everyone. So I guess we'll get started. A couple of more students may join us in a couple of minutes, but let's get started here. So we'll still be looking at chapter 13 today. And with one reminder that homework is due, number one is due on Thursday. Okay, so it's only like 3 days or so from now. If you haven't started working on the problems, make sure you get started. Okay, so I think that there's at least a couple of them are quite challenging. May take much more time than you would expect, but um, get started as soon as possible. And then I see many of you guys have already started working the problem, so that's a good sign. Okay. All right. So again, quick review what we learned last time. So last time we learned thermal expansion as well as ideal gas law. For thermal expansion, so pretty much like everything, every material will either expand or shrink according to the temperature change. So then the amount of the expansion, if this is one-dimensional linear expansion, then the change in length is equal to a coefficient, which is constant times the change in temperature T. Okay, actually this include the constant here in this equation. It also included original length of the material. But if you separate the original length of material out as L, then delta L, the change in length is equal to alpha times L. In this case, it says L naught, which is the same L in the two equations above, but that's the original length of the materials. Okay, times delta T, the change in material in temperature. Okay, so this alpha is called coefficient of linear expansion. And you can apply that to also to two-dimensional expansion. So then for a two-dimensional expansion, basically the change in area is approximately equal to twice of alpha, which is linear coefficient of linear expansion. So one-dimensional expansion coefficient times the original area of the material times change in temperature. Okay. Also, if you expand this to three-dimensional, then changing in volume of an object, that should be equal to beta, which is 3 times of the coefficient of linear expansion, okay, times the original volume times delta T, which is the change in temperature. Okay, so these are the expansion of materials in one, two, and 3 dimensions. Okay. All right, and then we talk about ideal gas law. So we'll start with a couple of assumptions. We started with a couple of assumptions that first the air molecules are small and they are far away from each other, so the interaction between them can be ignored. Okay, so and then you need 4 parameters to describe an ideal gas. So pressure, temperature, volume, and the number of molecules. Okay. We came to the conclusion that P is proportional to the number of molecules, and then it's proportional to temperature, but inversely proportional to volume V. So if you write it in equation, then P is equal to a constant called K times M, number of molecules, times T divided by volume. Okay, where if you rearrange the terms, then PV equal to NKT, where K, the constant K, is the Boltzmann's constant of 1.38 times 10 to the minus 23 joules per Kelvin. And in chemistry, pretty much people prefer to use moles of how many moles are molecules instead of how many molecules, okay, individual molecules. So 1 mole is the amount of carbon 12 atoms in 12 grams of carbon. And 1 mole is equal to 6.022 times 10 to the 23 molecules per mole. Okay, or in the case if the gas is single atom gas, then it's atoms. Okay, so this is also denoted as Avogadro's number in sub A. All right, so If you have m moles of gas, then the number of gas molecule is equal to m, small m, times Avogadro's number, m sub a. Okay. All right. And then if you rewrite the equation, so if you write n, the number of molecules as number of moles times Avogadro's number, so then PV equal to NKT becomes PV equal to small n Avogadro's number times K times T, where Avogadro's number and K, they are both constants, so you can actually multiply them and get a new constant number out of the two. So R, which is called R, which is called the gas constant R, capital R, Avogadro's number n sub a times K, all right? So that equals to 8.31 joules per mole times Kelvin. Then the equation of state for an ideal gas or ideal gas law can be rewritten as PV equal to small n times capital R times T, all right? So either PV equal to nRT or PV equal to capital N KT. Those are the two forms of the ideal gas law, okay? All right, so last time we didn't get a practice to use the second form. So this time, let's take a look on the example or exercise on the ideal gas law on the second expression. Okay, so basically PV equal to nRT here. So this one says how many moles of air are in an inflated basketball, assuming that the pressure in the ball is 159 kilopascal, the temperature is 293 Kelvin, and the diameter of the ball is 23.0 centimeter. All right, so there's unit conversion here involved. I'll give you guys a few minutes to solve this one, and then we can take a look at the solution together. Okay, in a few minutes, but you might want to use the conversion factor here. So from centimeter cube, because the diameter is given in centimeter, right? So then you will calculate what's the volume of the basketball. So basically, you are given D, so the volume then would be equal to 1/6 pi D to the Q, okay? If you are given R, in this case, you are given D, so you'll use this equation. But in another scenario, if you have the question, a problem that gives you R, then it's 4/3 pi R to the Q. Okay, so that's the volume for a sphere. All right, but anyway, in this case, you'll be calculating your volume. So that will be in centimeter cube. Then you will convert it into meters cube, right? So 1 centimeter is 10 to the negative 2. So that means 10 to the negative 6. Okay, so that's the conversion factor you might need to use. And then that's the equation for volume. You'll be using PV equal to nRT though, okay, in this case. And yeah, looking for this guy. Okay, how many moles? All right. So I've seen several responses in here. We can take a look at the solution together now. I think most of you guys got the number correct, but some of you guys didn't get the order of magnitude right. Okay, so let's take a look here together. You're looking for small m here, so you start from this equation. Okay, so then m will be equal to PV divided by R over times T. Okay, it gives you P. So keep in mind this P is given in kilocarbon. Okay, so it's 159 times 10 to the 3. Okay, so 159 kilopascal. Okay, so that's that one. Divided by R is the gas constant, 8.31 joules over moles times Kelvin. Okay, and then T is given as 239 Kelvin. Okay, so that's given. The only thing I'm not having here is the volume. So volume, as I say, you can use 1/6 times pi times d to the q, right? So d is given as 23.0 centimeter to the Q. All right. Now this is centimeter to the Q. So then you want to convert it into meters to the Q, right? Because you need to use SI units for each of the quantities here involved. So times from centimeter Q to meters Q is 10 to the minus 6. Okay. So meter Q over centimeter Q. Then here. All right. Now I have everything here in one place, but you might want to just calculate this one first and then do the conversion and then plug it in here, but it doesn't matter. Okay, so as long as you type in everything right, you should get this as 0.416 moles. Okay, so that should be the correct answer. So compared to C, where you actually didn't get it right. Okay, so first thing to check is if you get the kilopascal to Pascal, which means times 10 to the third. And then the second thing is to have this conversion from centimeter cube to meters cube. Okay, so which means times 10 to the minus 6. All right. Any questions you guys might have? All right. Remember, by default, you are muted, but if you want to speak up, you can unmute yourself, okay? So if you guys are clear, then let's move on here, okay? All right, the next section then in the textbook talks about kinetic theory, okay? So this is to make a connection between some microscopic quantities and some macroscopic quantities, okay? All right, so there's a question in the chat say, why is 10 to the minus 6? I guess that's referring to the conversion factor, okay? So let's see that. So remember, you are converting from centimeter cube to meters cube, right? So a centimeter, 1 centimeter is equal to 10 to the negative 2 meters, right? So then if you want to convert from meters cube, then you do Q on this side and then Q on this side, right? So then 1 centimeter cube should be equal to 10 to the negative 6 meters cube. All right. So that's why it's 10 to the negative 6 for the conversion factor. All right. Let me know if that answers your question. Okay, great. All right. Now let's move on to the next section. If you guys having no more questions on the previous section. Um, So on this one again, it talks about kinetic theory, which means it's relating some microscopic quantities to some macroscopic quantities. Okay, so for microscopic quantities, that means you use those quantities to describe a particular or a specific molecule. Okay, so for example, you say the position of a particular molecule or the velocity of particular molecule, right? Now, for macroscopic quantities, that refers to the overall, if you treat the whole gas as one system. So then you will have the pressure of the gas, right? Or the temperature of the gas, right? So it's collectively from all the molecules, all right? So let's see what's the relationship between those two types of quantities, okay? Now, we need to make some assumptions here because for real scenarios, for a gas system, it's much more complicated. Okay, so we'll be making some simplified assumption over here. So first, we are going to assume that the molecules of a collection of gas, if they are the same types of gas, they are identical. Okay, so they each will have a mass m, small m, okay, inside the container of volume V, all right? And then we are going to treat them as point particle. That means we are not going to take the effect of their volume. The molecule, each molecule has a small volume. We are not going to take that because for ideal gas, it's very thin, okay? So the molecules are small compared to the space they actually occupy, okay? The second assumption is we are going to assume molecules move randomly and always obey Newton's law. So that means we can use a Newton's law to describe their motion. Okay. The third assumption here we need to have is collision with each molecules and with all are elastic. Okay. So when the collisions are elastic, so then you do not lose any kinetic energy. Okay. So either it's collision between any two of the molecules or between one molecule and the wall. Okay. Now let's take a look. We are going to assume, so let me just go one more slice backward here. So we are going to assume your container is a cubic. Okay. So that means each side will have the same area and then traveling from one wall to the other wall in the same dimension. For example, the horizontal, vertical dimensions, they are traveling the same length of L. Okay. All right. So let's see here. So we are going to just focus on the X dimension. All right. And then because in the Y and Z dimensions, we can apply what the result we get from one dimension to those two because they are in all directions, they should have the same behavior. Okay. So here we are going to take a look just one particular molecule. Okay, so there may be hundreds or thousands of molecules, but we are going to just pick one. And then because each molecules, they behave the same, so then you can multiply that by the number of the molecules you have in the box. All right, so let's pick on this one here. All right, so this one travel to the left and then hit the wall on the left here. And then because this is elastic collision, so you'll bounce back and then traveling to the left, to the right, okay? So to the left, hit the wall, and then now it's traveling to the right, okay? So let's analyze what happens during this one collection of the molecule with the wall here. All right, so if there's collision between the wall and the gas molecular, so then there will be interaction, right? So during the collision, there will be force by the wall on the molecule, right? So that's why the molecule changes direction of the movement, right? And then there's also force on the molecule to the wall, right? So according to Newton's third law, action and reaction forces, right? So when the collision happens, there's a pair of action and reaction forces, all right? So let's see. So then because when this molecule hits the ball and it exerts force on the wall here, so then there's a force on the wall over here on this particular wall, okay? So then the pressure exerted by this molecule hitting on the wall, P sub particular one molecule should be equal to the force it exerted divided by the area of the wall, okay? So for the wall, because this is a cubic, so then the area for this particular wall should be the side times the side. So it'll be L times L, which means L square. Okay, so in the bottom here should be L square, right? Now for the force over here, you have to calculate this force by the knowledge we learned in the first semester, impulse and momentum. Okay, so let's see. So for this is not so obvious. So I'm going to just work on that. So the work on my paper over here. All right. So for the collision happens, all right, the impulse the wall receive I is then going to be equal to the change of momentum of the molecule. Okay. So maybe I should stop sharing so you guys can see this better. And I can share again after this. All right. It's going to be equal to delta P, which is equal to final momentum, right? Minus initial momentum. So in this case, the P means momentum. Okay, not pressure. I should say lower P then. Okay, so just to differentiate from the pressure capital P. All right, so final momentum over here, because you can choose to the right as positive, so then mvx, right? Initial momentum will be mv minus mvx, okay? So if you have a PowerPoint slide with you, you can refer to the figure in the PowerPoint slide. So final is mvx minus initial is minus mvx, because initially the molecule is traveling to the left and then hitting the wall and then bounces back. Okay. All right. So then this is positive minus minus, so it becomes twice mvx. Okay, that's the change in momentum or the impulse. Okay, the impulse the wall receive is equal to that. All right. Now, how much time does it take for this collision to happen for this particular molecule? Right? So it hits this guy, say it hits this guy at t equal to 0, right? And then it will go in this direction and then hit the other side of the wall and then bounce back and then hits this a second time, okay? So the time it takes for the wall to receive the impact from this particular molecule will be the time it takes for this molecule to go here, bounces back, right? So that will be so this is T0, the second time, T final, when it receives the second impact will be equal to that. So the time it takes delta P will be equal to, because this is the round trip, right? So it's traveling L distance and then coming back another L distance, so 2L divided by the speed of this guy molecular will be Vx, right? Because it's elastic collision, so the speed was not changing, okay? All right. So now you have the time, delta t, you have the impact impulse. So then according to how you calculate impulse should be equal to the force times delta t, right? So then the force should be equal to I divided by delta t, okay? Now from here, you see I is equal to 2 times mvx. Delta t is equal to 2L divided by Vx. Okay. So then you can see the 2 on the top of the here will cancel out the 2 at the bottom here. all right? And then Vx in the denominator of the denominator will go up there, right? So then you have mvx squared divided by L, okay? So this is your force. So the force exerted on the wall by each molecular per collision is going to be equal to that, okay? So this is the force, all right? So then if we go back to the PowerPoint slide, right? So force here is equal to mvx squared over L, divided by L to the square, okay? And then you can put the L square here, or you can bring this down because this is denominator in the numerator, so it goes down here. So then it becomes L to the Q, all right? And the mv square, this is in the x direction, v in the x direction, small v means speed, all right? Now L to the Q, it would be the volume of the cubic container, right? Because it's a cubic, so then L to the Q would be the volume. So the pressure on a wall by a particular molecule then is equal to the mass times the velocity or speed square in the x direction divided by the volume. Okay, so let's take this result down here. P, I'm going to just write on my paper here. We might refer to this in a little bit later. Small v actually means speed square divided by capital V means volume. Okay, a particular molecule. All right. Now, for a particular molecule, this is what you get. Okay, so this is what we get from the previous slide. P molecular for a particular molecule is equal to the mass of it times the speed in x direction square divided by V. We can so then for a collection of the whole gas system, you will have a box of the gas, right? So let's say there's M, capital N numbers of molecules. So for the overall pressure on the wall should be equal to M times pressure by individual molecule, okay? That should be equal to then capital M times Vx square, okay? Now, in here, from this equation, then P would be equal to, from the very left here, should be equal to mv squared divided by capital V from the very right here, okay? So then if you rearrange the term, you multiply both sides by V, you get PV on the left here, and then you get capital N mvx squared on the right, okay? Now, you can rewrite this guy. So you put the n, a 2 in front of n, then you should put 1/2 in front of mvx. Okay, so this is what it means here. So from here, you just simply rearrange the term, or actually doing a little bit modification on the term on the right side here. So then you get 2 times n times 1/2, okay, mvx, okay. You are doing this because 1/2 mv squared is the kinetic energy, okay, if you remember from the definition of kinetic energy. So then PV equal to 2 times m times 1/2 mvx squared, okay. And we should note that not all the molecules will have the same speed, right? We were making the assumption that each molecule have the same speed, but in reality, that's not true. So we should take average of this 1/2 mv squares for the kinetic energy term, okay? So then there's this subscript of AV, which means average kinetic energy, all right? So now you can see P is the pressure of the whole gas system, right? And V is the whole volume of it, right? So these two quantities on the left, they are macroscopic quantities, right? Means they are describing the behavior of the whole gas system. Now on the right hand side here, n is the number how many molecules, right? So that's the macroscopic quantity, and then v is the speed of each molecule. So that's also the microscopic quantities. Okay, so in this case, then we have the relationship between the macroscopic quantities and microscopic quantities, right? So we kind of relate them in this equation here. All right. I'm going to just pause for a second in case if you guys have any question. Okay, so let me know if you have any question, either unmute yourself and speak up, or type it in the chat. All right, if you guys are clear, we are going to just move on here. All right, so in one of the equations we had in the previous slide, I guess a couple of slides back, the last one in the 2 slides back, P of each molecule is equal to mvx square average divided by V. Okay, so in that case, we just look at the V, the velocity in the x direction, right? Now we should consider the other 2 directions as well, the y direction and the z direction. Okay, so because molecules should overall behave the same in all 3 directions, so then we are going to say the average speed score in x direction, y direction, and z direction, they are the same, right? And then for speed, because it's a vector quantity, so then if you look at the speed overall, then it should be equal to its x direction plus y direction plus z direction. Okay, so v square overall average should be equal to vx square average plus vy square average plus vz square average. Okay, so you should add those 3 up. All right, so then therefore the pressure in the gas is proportional to the average kinetic energy of the molecule, as we're showing in the previous slides, right? So in that case, if you multiply this P by N, P of each molecule by N, then that's the overall molecular pressure, right? And then you should be doing M here, over here. So this is where this N is coming from. Okay, divided by V is from here. Now mass comes down here, and then V square, okay? So V square, Vx square average should be equal to just 1/3 of the overall from here, right? Because X, Y, Z direction, they're all the same. So then if you want to just use the overall V speed, then Vx square means 1/3 of V overall square, okay? So then this gives you the pressure, overall pressure for the whole gas as this equation. So 1/3 of number of molecules divided by the overall V, and then equal to mass times V square average, okay? All right. Now, 2 slides back, we have PV equal to 2 times N and equals to 1/2 mvx square average, right? Remember this one from a couple of slides back. Let me just roll it back here from here. So it's actually this guy here. All right. Then we borrow this guy in 2 slides later. And then if you compare this to the ideal gas law we learned earlier, one of the expressions, one of the 2 expressions, so PV equal to NKT, right? And if you rewrite this term, just put the same, just mimicking the expression of this guy. So 2m times 1/2 kT TV, okay? Mimicking the 2m here by putting 2 here and then 1/2 in front of kT. So then PV is going to be equal to 2n times kT, 1/2 kT, right? So then you compare these 2 expressions, it's easy to figure out that this 2n of 1/2 mvx square average should be equal to this 2n of 1/2 kt, right? So then 1/2 mvx squared should be equal to 1/2 kt, right? 1/2 mvx squared, then it's the average kinetic energy in the x direction. That should be equal to 1/2 k times t, all right? So kinetic energy in one direction should be equal to 1/2 kt, right? And then in all the other two directions should be the same, right? So 1/2 mv y square average should be equal to 1/2 mvz square average, and those should be equal to 1/2 mvx square, okay? And then they should all equal to 1/2 kt, just because they should be have the same in each of the directions, x and y, z directions, okay? All right. So then kinetic energy for an average molecular gas molecular should be equal to 1/2 mv square, right? Average. And we know this should be equal to the 1/2 mvx square plus 1/2 mvy square plus 1/2 mvz square, right? So that means kinetic energy, average kinetic energy should be equal to 1 or 3/2 of kt, right? Because it should be 1/2 kt plus 1/2 kt plus 1/2 kt. The x, y, z add up, okay? So kinetic energy average for a particular molecule should be equal to 1 or 3/2 of kt. Now, I put the subscripts here as translational average kinetic energy, because for gas molecules, I don't know if you have learned this in chemistry or not. So if it's two atoms molecules, right? So it will have kinetic energy due to the movement. It will also have rotational kinetic energy because they are rotating around each other, right? And then in some cases, they are moving back and forth between the two atoms, okay? So then that's referring to another type of kinetic energy. But let's just treat them as point mass here for right now. Then we are ignoring the rotational kinetic energy and the other form, okay? So then just looking at the translational kinetic energy, okay? So it should be 3 halves of kT. And then if you are looking for the overall kinetic energy of the whole collection of gas, then you multiply that by number of gas molecular capital N, right? So then that should give you 3/2 of NKT, all right? And then remember, for ideal gas law, two expressions, we know that you can rewrite capital NK as small n and the R, okay? So then that's 3 small n R times T. All right, with that, then the average from here, you can see that the average speed square, that should be equal to 3 kt divided by m, right? You divide both sides by 1/2, get rid of 1/2 here, so 3 kt, and then further divide both sides by small m, so then you have 3 kt over m on the right hand side here, okay? 3 kt, you can write it as 3 capital N sub A Avogadro's number times K times T. Or actually, this is when you multiply both sides, both the numerator and denominator by Avogadro's number. Okay, if you do that, in the numerator you have 3 RT then. Okay, because capital N sub A Avogadro's number times Boltzmann constant will be your gas constant. Now, Avogadro's number times the mass of each molecule, that should be equal to your molar mass. Okay, molar mass in chemistry refers to the mass of 1 mole of substance, right? We use capital M, so that's molar mass. So then V square average is either equal to 3 kT over M or 3 RT over capital M, all right? So then you can calculate, you can take square root of this V square average to get the root mean square. Okay, so this root mean square means you're taking the square root of a quantity square average. Okay, so that's what it means. So that equal to square root of the V square average. All right, now V square average is equal to 3RT divided by capital M. Okay, so then root mean square speed of the molecular should be equal to square root of 3RT divided by capital M. Okay. Now, if you use Boltzmann constant, then so let me just write down here. So you know that V, you want to check on my video window here, VRMS is equal to either this guy, 3 capital RT divided by capital M. Okay, this means molar mass or molecular weight. I think they are the same. Or VRMS should be equal to square root of, if you use 3 Boltzmann constant T, then you should use small m. This is the mass of each molecular. All right. From here, capital M to small m is equal to capital M divided by Avogadro's number. Okay, that's the relationship. All right. So you might use this equation, or you might use this equation. Okay, depending on what quantities are known. All right. And then, as I mentioned, in addition to translational energy, molecular might have vibrational and rotational energies as well. Okay, so but that's not the focus of the lecture today. So I'm going to just skip that one there. All right. Now, if you remember, I mentioned a couple minutes earlier that each molecular might not have, usually they don't have the same speed. So there's a speed distribution for all the moleculars, right? So if the temperature for the whole system is like 300 K, then it probably have distribution like this. Okay, you might have zero, close to zero speed, and then up to very large speed, but the average would be around, say, 400 something here, okay, meters per second for the speed. And for different gases, they will have different distribution as well. So this is like one gas at that, or at different temperature, okay? So different temperature, you have different distribution, okay? So this refers to the same gas at one temperature and then the other temperature, all right? Now, it's also different if you have different types of gas, okay? So for example, argon gas have different distribution than helium gas, okay? But they will all have like kind of Maxwell distribution. That means some kind of this Bell function distribution of the speed, okay? All right, so that's section for kinetic energy. Let me know if you guys have questions. If not, then we are going to quickly look the next two sections here. The next section talks about phase changes. I think you guys all know that a substance have different phases. For example, water have phases of ice and liquid water, and then also as steam, vapor. All right, so they are commonly there are three phases of water that we see often, but water itself is a very complicated material. It actually has more than I don't exactly remember the numbers, but it's about 10 or more different phases. Okay, but most common ones are liquid as liquid water, and then ice as solid water, and then steam as vapor water. Okay. All right. So different state of materials are called phases: solid phase, liquid phase, and vapor phase. Okay. For materials, let's say certain materials. Okay, if it's in the gas phase, if it's diluted, then you can use PV equal to nRT to describe. You can treat it as an ideal gas, right? So then you can plot from here. If you plot its volume versus temperature, okay, So from ideal gas law, you can rewrite, so then V equals to Nr over P times T. So that tells you V and T are proportional to each other, right, in the gas phase. So temperature increases, the volume of it will increase. Okay, then it should be a linear, all right? So it's a solid red here. But as temperature goes down, for example, for steam, temperature goes down, then steam will become liquid, right? So then it no longer fall in this red line here. It will have a phase change from, say, vapor to liquid. Okay, so then you drop the volume, now no longer proportional to the temperature. All right, and then temperature further goes down, it becomes solid. Okay, so then the volume again doesn't behave in this linear relationship with respect to T. Okay. All right. Now, if you plot P versus V, again, starting from PV equal to nRT, if this is a gas phase, then you obey this formula, right? So then you'll see PV equal to nRT if you are fixing temperature T, the meaning temperature doesn't change. If you are just change P of V, then P times V should be a constant number, right? So then in that case, if you plot P versus V, it should be a parabola function, right? Like something like this red one here, T5 and the temperature T5. And then if you have a different temperature, then curve changes slightly. So T4 here, all right? Now, if you decrease temperature again, then it might not be ideal gas, but you can see there's a kink here on the curve here. So the fact that it's not a smooth curve, that means it's not ideal gas, okay? It's not simply PV equal to nRT. All right, you can further decrease down, so then it will change. If there's further change in the curve, you might be in the condensation process already, okay? Similar over here, P versus V. All right, this is probably for a different gas here. So it starts with ideal gas, which is smooth curve, then not so ideal. All right, and then there's critical point here, phase transition. All right, so for critical point, there are a couple of critical points. One is called critical temperature, which means above which liquid cannot exist. Okay, so then above certain temperature, the material will be just in gas form. All right, so that temperature is called critical temperature. Also, similarly, for certain for a particular pressure point is called critical pressure. So then it's the minimum pressure needed for liquid to exist. Okay, so if pressure is too small, then it might be just gas. Okay, it will not be liquid. Okay, so just terminologies you have to remember or maybe get familiar with. All right. And the table here lists the critical temperature and critical pressures for several substances here. All right. If you need, then you can look them up here. All right. Now, if you plot P versus T, previously we have looked at P versus T, P versus V. We look at V versus T, volume versus temperature first, and then we look at pressure versus volume. Now, if you look at pressure versus temperature, so this is the a plot called phase diagram of a substance. Okay, so on the phase diagram, you can see under what condition what would be the state of the substance. For example, solid state will be here, liquid will be in this range, and vapor will be in that case. Okay, so this is a simple phase diagram for water. Okay. All right. Next, we are going to look at liquid and gas in equilibrium. Okay, so when that happens, then you have the same amount of water. For example, if this is water, okay, becomes steam, and then the same amount of steam becomes water. Okay, so say probably like 0.1 moles of water becomes 0.1 moles of vapor, but then vapor 0.1 vapor becomes 0.1 water. Okay, so when that happens, if you reach at net equilibrium, then this is the boiling of water. Okay, and that position. Then when that pressure is reached, the pressure at that particular condition, under that particular condition, is called vapor pressure. Okay, it's defined as the pressure at which a gas coexists with its liquid. Okay. Vapor pressure curves. Okay, so it changes. All right. So vapor pressure of water, this is a part of vapor pressure of water, okay, versus temperature. So under different pressure, for example, for sea level, we are having atmospheric pressure, okay? So then water boils at 100 degrees Celsius, all right? Now, if you have pressure cook, actually water will boil at around 120 if this is 2 times of the atmospheric pressure, 2 atm, okay? So then your temperature is higher. So that's why if you use a pressure cooker, it actually can use less time to cook something, right? Because the temperature is higher, right? Now, if you go mountain climbing and then you are having, say, lunch, picnic over there, you want to cook something there. If you are at higher elevations, then the temperature actually drops. Okay, so let's say like at 10,000 feet, it's only about 90 degrees. So then you want to cook longer, right? So that's why in Denver, because it's higher in elevation, so that rule doesn't really apply. You might want to cook your egg longer because temperature boiling and water boiling is actually smaller. Okay. The next topic here is called partial pressure. I think you guys probably have learned this in general chemistry. But it's called Dalton's law. For example, for room air is made of primary oxygen and nitrogen. So then according to left, mole fraction. So then part of the overall pressure comes from oxygen and then part coming from the nitrogen. Okay, so then they add up to get the room atomic pressure. Okay, that's according to their mole fraction. Okay. All right. The next here is the dew temperature or the dew point. Okay, just remember this last line here. The dew temperature, at dew temperature with relative humidity is 100%, okay, where the condensation may happen simultaneously. On the last slide here, this is simply one example that if you want to know the temperature at which water is boiling, then you have to look it up on the table, like what's the vapor pressure. Okay, so for example, at sea level, it's 100 degrees because vapor pressure is this guy here, 1.01 times 10 to the fifth. Okay, so I'm going to just give you the answers for this two. You guys can look up the table. Just simply look at the table. So for A, at that vapor pressure, 8.95, you're looking at the table over here. So that would be 95 degrees Celsius. Okay. For B, when the atomic pressure is 7.01 times 10 to the 4, then the temperature will be at 90 degrees, the boiling temperature. All right. So simply look at the table here and then find the corresponding boiling temperature here. Okay. I'll stop here for today. Okay, let me know if you have questions before I let you go. Otherwise, I will see you guys on Wednesday. Bye.
Thank you.
You're welcome.